Conductors versus insulators. Here we go. We're going at review pace here. Okay? So not to bore you. So a conductor, when it experiences an external field, it polarizes over the entire object. So like the sea of electrons are able to, okay, versus an insulator, the molecules themselves polarize, but the electrons are not able to leave unless you make this electric field so great that you're able to dissociate the electrons, and that's dielectric breakdown. Like full circle there, yeah. Which does not usually happen in an AP question, unless it specifically tells you. Okay, so don't assume. All right. Yada yada yada. So in here, the net electric field is equal to 0. You have the external, but then you have the internal. So this conceptually kind of anticipate this is going to be a thing on the AP. Like, oh, there's no electric field. Oh, there is. There's two of them. Knowing that that the net electric field is equal to 0. Okay? Versus here, there's a weaker electric field inside the insulator due to the electric field produced by the polarizing molecules. So there's excess charge. The conductor always goes to the outer surface. Insulator, it's wherever it was charged. It's stuck there. So distribution of charge. Conductor, they go to there's a higher concentration of points. So you have a higher electric field there. Electric potential, though, is the same throughout. Insulator is just wherever they've put it. It will state it as here's what it's doing. Usually it's like a uniform density or some kind of function density. Yep, like that. Okay, so here we've hit this slide before. So hardcore calculus. So this, you need to divide it up into small like point charges and then add them up. You have to do this with like a charge rod or like a ring. But a ring, you can do this, and like an arc of charge, you can do this. Find the electric potential. Once you find the electric potential, then you can take the negative derivative to find the electric field. It's way easier to find the electric potential using this because there's no direction. It's just a scalar. Okay? So Gauss's law, this is a shortcut. You use Gauss's law, Gaussian surface. And then once you find the electric field, then you can integrate that. Usually starting where electric potential is equal to 0. Usually that's infinitely far away. They usually define that for you and bring it in. So this is kind of the summary of the math that we've done. Okay, big picture. So here are some specific classic examples of what you will see. You've got uniformly charged hollow or solid sphere that's on the surface. So these are all can be condensed down to point charges on the outside where R is greater, like outside of that, and on the inside a conductor is equal to 0 and inside a insulator is equal to 0 if the charge is only on the outside, hollow planet stuff. Good? Okay. And so when we integrate this, we find this behaves like a point charge on the outside, and on the inside there's no electric field, so the electric potential remains whatever it was on the outer rim. Good with that? Okay, and so those are your graphs of your electric field as a function of distance away from the center and electric potential. Assuming these are positive charges. Okay, so it's uniformly charged throughout the volume, and a conductor, that's impossible. On the insulator, you need to find, so you pretend like this is all charged, like you take all the charge of it, add it together. But then on the inside, you need to do this hollow planet thing, this ratio of charge. Oh yeah, okay, here we go. We're going to find the charge on the inside. So the charge on the inside is lowercase q, capital Q is charge on everything. Bring that over, cross that out, pop, you get that. If you have a function of charge density, volumetric charge density. So let's say it says is equal to 4x, 4r, sorry. Then what you need to do is say that that's charge over volume, and that is going to be the surface charge density of a sphere times the little width of dr. Okay, so then you bring that over here, so 4 pi r squared dr, and then times rho is equal to dq, and then plot that into there. Then you would integrate that from 0 to wherever your r is to find the charge enclosed here. That's a pretty involved problem. Probably should add a slide for that. Okay. So everybody, you see how to like dissect that. Okay. Questions there? Yeah. So this is like the full-on, like, what do you do to find use the integral of the electric field as a function of position? We're going to figure out where you're trying to evaluate the electric potential at. I call that the final position. Choose a point. Electric potential is 0. Often it's infinitely far away. That's your initial position. Establish your coordinate plane. Okay, so like you usually just make that point wherever the center 0, 0, and we're just going to focus on the x-axis, keep things simple. Technically, here's all the vector notation of that. Electric fields in a vector. What you're integrating is vector. That's captured by this final position minus initial position. If you're starting here and going this way, that's going to end up making this negative. You don't have to put a negative there. That's just captured by this. Okay. And then there's a negative out there just because that's the equation. Yeah. And remember, if your function, the equation that describes the electric field changes as you go from instantly far away to where you're trying to evaluate, you need to break that up into stages so that the electric field is consistent function between your integrals, and you're adding all that up.
So if you're finding the voltage like between two objects, can you just go from this object to this object and not involve?
Yes. So, you ever hear that question? this is specifically for capacitors. If we're just trying to find the voltage between two plates, you can declare one to be 0 and the other to be, okay, so it's just finding the electric potential difference between those two spots. Good with that? Sure.
What would be an example where you have to use the equation at the very bottom, like where the electric field changes?
So if you had a charge sphere and then this going from here, like here, the electric field inside this conductor is 0, and then this has some kind of charge, this has some kind of charge. That would be an example of that.
And what would it be asking you about the voltage of?
What's the electric potential at that location there? And so, in my mind, the way that I kind of go through it is I'm double checking with the landscape, the contour of the landscape. Like I'm trying to visualize that. Like, do I have mountaintops? Do I have sinkholes? Where's the plateaus?
You go from the outermost side, right?
Yep. Because you're starting infinitely far away going in.
Yeah, and then you hit the, like in the middle ring.
Yep. This guy to this guy.
That guy.
Okay.
So you do the outer edge to the point of the side. He's not getting one.
Right. So like, let's say the outer rim is like 100 volts. Yeah, say that. And like right here, because you're like this far away, is like 90 volts. This whole surface in here is 100 volts, not 90. Good with that? Okay. So it's determined by the outer, not the inner surface. Okay. So that's me integrating uniformly charged. Insulator. Find electric potential on the inside. Okay, so this would be another example where the electric field changes its function. Okay. So you get a electric field and electric potential look like that. Okay. So charge ring. You're definitely going to want to do electric potential. You don't even have to do calculus because they're all the same distance away. The charge is all the same distance away from this. So it's just the whole charge, some distance away. That's just your hypotenuse. Like that. Okay. And then once you have that, you can integrate it. Sorry, take the derivative of it, which is way easier than doing the calculus cosine. Okay. Uniformly charged disk. I've yet to see this. You're right. It's not on tomorrow's or this week's test, but it could be. It could very well be on the AP test. Okay. So, to just divide it up in concentric rings, and you're just adding those up. And then once you find electric potential, then take the negative derivative, find that. Linear line charge. So Gaussian surface is a cylinder. Its It's just this outer surface, not the end caps that have flux going through them. So your area is going to be 2 pi r times the length. Charge enclosed is charge density times the length. The L's cancel out, you get that. And then we integrate and we go, oh yeah, we can't do from infinity, so we go from the inner surface. So this once was one-dimensional, now it becomes three-dimensional when we evaluate this from R. So we're just saying it's really long. So we're just looking at linear charge density. We're not going to get tripped up the fact that it's three-dimensional. Like, oh, there's linear. Like, how do I do volumetric? Don't worry about it. Just linear. And then you look at the three-dimensional shape of that inside there. So if it's coaxial cable, you're going from RA, which is inner, to RB.